Good morning and very warm welcome from me again to the morning session. We will have two very interesting talks. The first speaker is Wojciech Kamiński from Warsaw University, and he will speak about isolated horizons and apparently even extreme isolated horizons. Please go ahead.
So can you hear me? Yes, okay. So I would like to thank the organizer for invitation and especially for suggesting the topic. Because apparently if you look at something that you were working long time ago, then you have always some maybe new ideas. So thank you very much. So maybe let's start with some small introduction. So why I agree to speak about isolated horizons? Because recent, especially extreme isolated horizons, recently there was exciting progress in the field, especially exactly in this extreme case. The extreme case corresponds to the surface gravity equal to 0. And this is interesting subject because these extreme isolated horizons constitute a hard part in the classification of stationary black holes. So this classification is one of the cornerstones of GR. And apparently, they can be created in physical processes. So one could expect that because of the third law of thermodynamics, you cannot create the black hole with the surface gravity 0. But apparently, there are some works that showing that it can be obtained by throwing some matter into non-extreme black holes. And moreover, they have application in quantum gravity. So the goal of my talk is to present recent development in the topic. Okay? And so maybe let's remind the theory of extremal horizons. So suppose that we have a null surface in our space-time that is vibrated by the null vector, so the flow of the null vector. And of course, because it's null surface, we have the degenerate metric that is a restriction of the metric from the spacetime. So this L is the degenerate direction, and this pi is a vibration. So we assume about this space of rays that it's a compact manifold. So as Abai mentioned in his talk, the non-expanding condition under some mild assumption on the stress energy tensor is equivalent to the fact that this degenerate metric is leader-act by this vector L. And this means, in fact, that this G tilde is a pullback from this sigma of the metric, and this metric is already Riemannian. So in fact, this G tilde is a pullback of the normal Riemannian metric. So because of this condition, the covariant derivative, our space-time covariant derivatives restrict to the tangent space of this edge, of this horizon. And we have some additionally to this metric, we have connection. So this connection is metric in torsion-free, but because this metric is degenerate, it's not determined uniquely. So this condition of being isolated horizon, and it's a stronger condition than the weak isolated horizon of the Abai talk, is that this connection is leader-act by L. So one should think about that as a like higher order killing condition on the horizon. So all these theories to describe like local notion of being a killing horizon, but only to certain order. Okay, one can introduce, so because this connection is metric, it's also preserving this L up to some rescaling, and one can introduce rotation form by this equation. And the self-acceleration, so the surface gravity is equal to the contraction of this L with omega with L. And as I mentioned, connection is not uniquely determined by the metric, but it's also not uniquely determined by this omega. So omega and G, it's a bit weaker data than this connection. Okay, so now one can think in the abstract way, so one can forget about space-time, and one can think about isolated horizon data abstractly as just this manifold with vector L, G, and connection satisfying these conditions. Okay? So there are two cases. So we have this surface gravity, and from these conditions follow that it is constant on H. And there are two separated cases that are different. So the non-extreme horizons, when this kappa is non-zero, in this situation, if we impose Einstein equations, then it's turned out that in fact this connection is determined. So if we have omega and G, then connection is uniquely determined by the Einstein equations and the condition that it's lead direct along the horizon. It's even more. So if we asking whether such data appear as in some Killing horizon, then it turned out that this Killing horizon is unique. So it always exists, such Killing horizon, and it's unique, and it's not surprising because we can think that we taking some bifurcation two null surfaces, we imposing this metric here, and we just evolve Einstein equation from the null conditions, from the null initial data to this blue region. Of course, it may, some singularity may form. Of course, we cannot evolve it into this dark region, but if we assume some analyticity, then we can analytically continue it from this blue region to the dark region. Of course, also singularity may form, but locally, it's just unique spacetime. Okay, so but in the in the extreme case, situation is completely different. And if we impose Einstein equation, instead of allowing us to determine the connection, and maybe if we looking for the embedding in the Killing spacetime with the Killing vectors, higher order derivative of the metric in transverse direction to the horizon, in this case, it turned out that it's just giving some constraint. So this omega, maybe let's look for a moment back. So this omega contracted with L is a surface gravity. So if it's zero, then omega is a pullback, like the metric was, pullback of something from the sigma. So in this extreme case, in fact, omega is pullback of some one form from this space of rays. And this non-tilde omega, that's why I denoted by non-tilde, and non-tilde G satisfying this equation. So this connection here is with respect to G, it's just the Levi-Civitas connection. This is the Ricci tensor for this metric G, and so on. So I added these strange dots because one can also add some matter, and then this is some non-zero contribution from the matter. We've seen this on the Abai talk. In fact, in his case, because it was weakly isolated horizon, this zero was non-zero, but there was redirect of this S. Okay, and so this is not allowing us to determine connection. The connection need to be determined by some other order constraints, and in fact, it's not determined, but it's constrained. And moreover, what is interesting, one can associate with solutions to this extremality equations. I would call it extremality equation. One can associate some canonical, let's call it canonical spacetime in which it embed as a horizon. It's called near horizon geometry, and it has such nice form, and some certain spacetime. So I will come back to this this form later, but it's important that we always can embed it. It's these near horizon geometries were not invented. Okay, so they are obtained by the Garrosh type procedure applied to some spacetime with extreme horizon. But for us, important is that it's mean that we would like to have non-uniqueness. So if this omega and G uniquely determine the spacetime in which it is horizon, then it would be not really interesting because it would be this near horizon geometry, and these are not spacetimes with nice asymptotic properties. Okay, so in this case, we want, in fact, that embeddings are not unique. embedding in scaling space. Okay, so let's look at this equation. So this will be the main character in my talk. And so it was analyzed. For example, one can find all axisymmetric solution on a sphere. And it turned out that this equation alone allow us to determine that all these equations just correspond to the horizons of the curve. It was generalized also to higher dimensions. So this equation is in arbitrary dimensions too. So in higher dimensions, if we impose sufficiently many symmetries, then it turned out that also one can find all the solutions. And moreover, there is something very interesting happening with this near horizon geometry spacetime. It has higher group of isometries than expected. So this group of isometries of near horizon geometry, so it depends what one expects, yes? But there is this L, there is some boost killing vector, but apparently there is also some hidden killing vector that you cannot easily write down. Okay, and all of that is based on the fact that such omega is related to a killing vector by this strange formula, so some gamma bigger than 0. So maybe let's make the small summary. So this, I told that in order to highlight some differences between extreme and non-extreme horizons. And for the case of extreme horizons, we have intrinsic constraints. So they're intrinsically constrained. And it's contrast with non-extreme case, when only we can constrain it by some global property of the spacetimes. Okay, so this leads maybe to the structure of my talk. Okay, so I would like to show you progress on some natural questions. So from what I told you, one can think, so for example, whether one can answer all the questions that are asked in the classification of black holes in the case of this extreme horizon by this single equation, this near horizon geometry equation, this extremality equation. Okay, and so this exciting progress was in fact in the, so maybe I will just, so first of all, there is this rigidity problem. So the question is whether, in fact, in every for every extremal horizon, we have this additional symmetry. So then, so this is based on, okay, it's an analog of the rigidity theorem in the classification of black holes. We have also this staticity problem. So it turned out that this killing vector, it has vanishing twist, so it's static if the exterior derivative of this one form is 0. And on the other hand, this omega, it's a measure of the rotation of the black hole. So a black hole is non-rotating if omega is 0. So what one expects, that if d omega is 0, so if it's static, then in fact it's not rotating. So this would be natural conjecture. Okay, so and this is true in the classification of black holes. So question is whether from this extremality equation we also get this implication. So then of course, so there is a famous Hawking theorem showing that every black hole in 4 dimensions is a sphere. So the cross section of the horizon is a sphere. So one can ask similar question for the solutions of this extremality equation. So one can ask whether sigma need to be a sphere. And the last I already mentioned, so it's apparently we have some ambiguity in the embedding of our horizon as a killing horizon in spacetimes. So one would like to classify possible spacetimes with the isolated horizons as killing horizons, and moreover classify isolated horizons with given this near horizon geometry data. So this near horizon geometry, so I made the mistake. So this near horizon geometry data is just this omega and g, so one form on sigma and metric. satisfying this equation. Okay, so as I mentioned, so there was gigantic progress on solution of this problem, and so in fact, so these isolated horizons, they were studies, extreme isolated horizons from the IP 2000, so already 20 years. And for 20 years, people didn't know whether it's true that there is additional symmetry. So it was really hard problem, but apparently, nice hard problems has nice solutions that are not as hard. So this is the case exactly in this for this rigidity problem. And maybe let us look for a moment on this. We know that if K is a Killing vector, that it satisfies also some Laplace equation. So we are in the signature Riemannian, so in the Lorentzian it would be some wave equation. So this wave equation is obtained just by taking the divergence of a Killing equation. Okay, but what is interesting that on compact manifolds, and we assumed here that the sigma is compact, it's also other way around. So if K is, let's say, divergence free and it satisfies this, I would call it Killing harmonicity, then it's also the Killing vector. And why it is like that? So it's very simple argument. So it's the same argument as for the case of Laplacian. So we know that there is many harmonic functions, but apparently on compact manifolds, every harmonic function is constant. So why it is like that? It's just simple integration by parts. So if we integrate by parts, we see that we have some integrand of something positive. So this integrand needs to be 0 in every point, so phi needs to be constant. So very simple generalization of that giving this. In fact, one can say even a bit more. So one don't need to assume that this box of K is 0. It's enough to assume that this box of K can be written as a derivative of some function plus a vector that is perpendicular to K. And if K is divergence free, then it will be the Killing. Okay, and now, so what this progress was, so in fact, a year ago, Kamiński and Loops'24, they found remarkable identity. So they assumed that K is of this form so this form is important because it's allowing us to obtain this enhanced symmetry of near horizon geometry. Okay, so if we assume that K is like that, so of this special form for arbitrary gamma, then we have such equality. So it's direct computation. One can just plug it, half an hour compute, and one gets this result. Okay? And we see that if we manage to choose this gamma in such a way that this term is 0, so the K is divergence free, then we'll have exactly point in our small lemma. Yes, so if we do that, of course, it's not easy to find such gamma. So it's amount to finding a solution of such equation. So it may look difficult. So this is some elliptic operator. So on the compact manifold, elliptic operator has discrete spectrum, so it's already good. Maybe there will be the solution, but why 0? Why there is eigenvalue 0? But there is an interesting fact. So this L is not self-adjoint. So there is also this L dagger. So L dagger is just we reverse order of the derivative. So this L dagger has known eigenvector, it's 1. So because if we apply this to 1, we are already getting 0. So whatever after that coming, it's also 0. So 0 is in the spectrum of L dagger. But the spectrum of L is completely conjugated to L dagger. Okay, so 0 is real number, so it's also in spectrum of L. Okay, so very good, we have such gamma. So if we plug it here, we're showing that k is a killing vector. So very nice, I would say. Okay, so of course, there is something more. So as I mentioned, this gamma will also serve for this enhancement of the symmetry. So it turned out that it's important that this gamma is non-zero, it's positive. And in fact, there is some deep theorem. So this is something, okay, so one always learns something new. And it turned out that if we consider such equation, then we can think about that as a generator of some Brownian motion with sheet. So this omega is a sheet. And this equation is turned out that it will have some equilibrium probability distribution. And this gamma, so the zero eigenvector, corresponds exactly to this equilibrium. Of course, the proof is a bit different. The proof uses some quite interesting functional analysis called the Krein-Rootman theorem. But one can show that this gamma, so solution to this equation is zero, so this equal to zero. And there is no other solution to this equation. So this is the only. Okay. Okay. So, okay. So, but that's of course not all, because we would like to know that this omega is in fact preserved by this case. So now we only know that we have the killing vector. So to have symmetry, we also need to know that omega is preserved. But if we look at our identity, it simplifies. And it simplifies to something that if we write in terms of forms, we're recognizing as Cartan formula. So Cartan formula is telling us that this Lie direct omega is in fact d of something. This something is written here. Okay, so if we apply this Lie derivative to this, okay, so I was changing the names in the last moment, and this NHG should be this extremality equation, but okay. Okay, and we get this equation that if we look for a moment, always not there either. So then it's very similar to this, and the same way we can show that the only solution is u equal constant. And if u is constant, then this Lie direct omega du is zero. Okay, so this is the theorem that every non-static solution to this extremality equation possesses a killing, also preserving omega. So why non-static? Because it may happen that this k is zero. So we obtain k, but why it's not zero? So zero is of course also a killing vector. Okay, so now it's better here. Okay, so but it's non-static. So if k would be zero, then omega would be exact. So that's why this non-static assumption. Okay, so maybe let's go to the staticity problem, and I need to a bit hurry. Yes. So in this case, it's good first to look at the really simple example. So of course, this extremality equation we can also solve in dimension 1. Okay, and then we have a surprise. So in dimension 1, we have the metric always can be written in this form, the form in this, and we have this extremality equation simplifies, and the only periodic solution, so there are now some non-periodic solution, but if we assume that it's on some circle, then the only solution is this. Okay, it's static, and the omega is non-zero, at least for lambda smaller than zero. So for cosmological constant smaller than zero, we have some static solutions that are rotating. That's okay. So of course, every solution to Einstein equation, it's also solution of this extremality equation with omega equal to zero, and it's also static. However, we can also create new solutions if we take this 1 and 2 and combine them. So we can just take the Cartesian product of these two solutions, and it turned out that it's also a solution to extremality equation, also static. Okay, so if we have that, we can take the universal cover and divide by some subgroup of the isometries. And we have the solutions that are locally like that, but with some non-trivial topology. Okay, of course, if lambda is 0, then this is also omega equals 0. In this case, just omega is 0, and it's just equation 2. Okay, so question is whether these are all static solutions, and this the answer to this question was first provided by Kruściel, Rial, and Tont in 2004. And recently, only recently, it was noticed that for lambda smaller than 0, it's a bit more complicated. Okay? So, but we can look at our remarkable identity. So, okay, and if we look at that, okay, so then it turned out, of course, this k might be 0, but the identity is still true, and omega is 0, so this vector A is 0. So it turned out that this v is constant. So for lambda smaller or equal to 0, this equation has only constant solution. So it's a property of Laplacian. So Laplacian does not have a positive eigenvalues. Okay, so but if it's constant, k is proportional to omega, and this omega, so this rotation form, in fact, it's not only twist-free, so we assume static solution, but also it's just a Killing vector, so it's just covariantly conserved, covariantly constant. Okay, but this, if one think for a moment, what does it mean to have? So this is very strong condition for the space-time, or for the geometry to have constant vector. So it means that we have, in fact, the splitting. So we have, it can be written at least locally as a product of two spaces, and omega is just the vector in the direction of R. Okay, then global result follows by considering universal cover. So it's turned out that we can classify this solution, and for lambda equal to 0, omega is 0, as we would like to have. But for negative cosmological constant, there are some solutions that are rotating, static but rotating. However, the most physically interesting case, n equal to 2, it turned out omega is 0. So maybe let me say more why this n equal to 2 is special. And for that, we need to say something about this topology problem. So in dimension 2, Riemannian geometry is just complex analysis plus scale. So we can, and it simplifies things, because if we introduce projections onto anti-holomorphic covectors, and this projection, this epsilon, so the Levi-Civita antisymmetric symbol has two indices, so you can use it for creating operators. So these projections, so we can project omega and covariant derivative on these anti-holomorphic parts, and you can apply 2 times this projection to this extremality equation, and you're getting something very simple. So in fact, this equation is true also in the presence of the Maxwell field. So in 4 dimensions, you can get, so this equation is like more general, yes? So it's not only for this extremality equation in the vacuum, but also if the Maxwell field is added, it still holds. And so then, if we want to look at, so we looked at our old papers when we proved a bit weaker version of this fact. But in fact, with a small amendment, one can show that if we have solution of such equation, then on the genus surface bigger equal 1, so except the sphere. So this is on the surfaces of the genus bigger than 0. Then this f need to be 0. So if this pi is 0, then omega is also 0. Okay, so we have such nice theorem. that if we have the solution of this extremality equation with the Maxwell field, even with Maxwell field, on the surfaces of non-zero genus, then omega is 0. So this is the version of the topology theorem, because then one can also check that this lambda need to be smaller than 0 in this case. So there are, let me mention that there are also some constraints for higher dimensions, but they are weaker, and it's one expected because also you have weaker constraints in the case of this classification problem. Okay, so maybe the last thing. So how to approach this problem? And on that, it was also a bit progress very recently. So let's consider, so if we are thinking about embedding, of course, it's good to use some coordinate system. So the natural choice, and it's quite general, is to use so-called null Gaussian coordinates. So you can always write your metric in such a form. So why here there is this rho square? Because the surface gravity is 0. And here is the rho because of these null Gaussian conditions. And these null Gaussian conditions mean that d over d rho is tangent to null affine geodesic. So this is the definition. Okay? And we want that this d over dv is our killing vector. So there is still freedom, gauge freedom in these coordinates. Of course, there is one part of this gauge freedom is the diffeomorphism on our space of rays of this sigma, so this x. But also we can shift, we can add something to this v. So we can shift this coordinate v, and it's changing the direction of this initial d over d rho. So of course, if you're sending the null geodesics, you need to know in which direction you are sending them, and it's not uniquely determined by the condition that they are null and the product with the DL is 0, it's 1. Okay, but the second gauge freedom can be partially fixed by assuming some condition on the divergence of the measure, so on the expansion in the perpendicular direction. Okay, and this we can always achieve on the compact manifold. Okay, so how one can solve, how one would like to approach this problem, and this is very general method. So applied in the Bondi gauge, one can also apply it in the Pfefferman-Graham expansion. So we expand all these functions, g, omega, and f, in the Taylor series in rho. We write Einstein equations, and we look what is the recursion relation that we obtain. So we're hoping that we obtain a recursive equation that will allow us to determine this g, f, and omega. Okay, so one can do that, and it was done in this paper. Okay, and if one do that, then one finds the following structure. So structure is the following. So of course, we have many parts of the Einstein equation. We first using only some of them, and then the rest will follow from Bianchi identity. So we're using some of the Einstein equation to determine some of these expansions, and the rest follow from Bianchi identity. Okay, and if you look at the one part, you're getting equation of this form. So you have some differential operator acting on this Gn part of the expansion of the metric and giving by the lower order terms. This lot is some mess, but we don't need to care much about that because it's only depending on things that we already determined. So on Gn minus 1, Gn minus 2, and so on, and omega n minus 1, Fn minus 1, and so on. But once, suppose that we are able to solve this equation, so find this Gn, then this Fn and omega n are determined by algebraic equation. So you can just write explicit formula. Okay, so now we know how to approach the problem. At least there is an idea. So we just solving to order n. And then in order n plus 1, we need to determine Gn plus 1. satisfying this equation, and then Fn plus 1, omega n plus 1 is determined. So maybe a small comment, it turned out that if we look at the first term, so it's always good to look at the few first terms. So the first term contains information equivalent to the choice of connection. This first equation was determined by many people, and this relation, I think it was in this paper. Okay, so with this choice of gauge that I mentioned, these AN are elliptic operators. And what does it mean? Oh, it means these elliptic operators have finite kernels and co-kernels. So such equations will only have a finite space of solution. So it's a finite equation. Yeah? So this Gn, it's maybe not uniquely determined, but it's determined up to some finite dimensional ambiguity. Okay, but also it may have some finite co-kernel, finite dimensional co-kernel. So if it has finite dimensional co-kernels, then you have a finite set of the constraints. So these constraints, of course, will obstruct your ability to solve this Gn. So in every step of this expansion, so we have only a finite number of ambiguities and finite number of constraints. It's still not good, yes, because especially these constraints, so ambiguities, we would maybe be even happier. So we would just, if there would be only ambiguities, we would know that in every step we can just choose one of the options and we go further and further. But these constraints, they in the next step, they were say that our previous choice was not good. I'm almost finished. Okay, so so it's turned out that there are two qualitatively different situations, and they depend on the sign of cosmological constant. So in the case when we are in the Sitter case, it's turned out that this AN has vanishing kernel and co-kernels for n bigger equal to 2. Okay, and this A1 has one-dimensional kernel. We are really happy, because if it would have always kernel 0, then we would be able only to embed our horizon in this near horizon geometry. So if it would be like that, we would be not happy, because this near horizon geometry, they are physically not very interesting space. But we have here this one-dimensional kernel, and this kernel corresponds exactly to the fact that we can embed this extreme horizon in the Schwarzschild instead of the near horizon geometry. Okay, so this is the positive version of so it's satisfying really the method that I showed on the last slide. We can apply here and we're getting a very, very nice answer. So we have uniqueness of the Schwarzschild. Okay, however, if we look at the kerr for lambda equal to 0, then it turns out that every AN has non-trivial kernel. So from this point of view, our method completely fails. So we would like to have some kind of uniqueness. And it seems that if we think that really we can always put everything, so we can, if we believe that there is no co-kernel, so there is no obstruction, fortunately probably there is, then we would have completely non-uniqueness of the embedding of the. Okay? So maybe let's summarize. So, so these extreme isolated horizons are now better understood, especially for this lambda smaller equal to 0, because then we have also knowledge about the staticity theorem. So let me remind you that for lambda bigger than 0, as far as I know, there is no information about, so there is no equivalent of the staticity theorem. So we don't know whether extreme horizons, static extreme horizons with lambda bigger than 0 are rotating or not. Okay? So let me stress that in the case of the presence of electromagnetic field, in this moment we have only some small results for n equal to 2. So if you would like to have it in the higher dimensions, you don't know anything. So there is no information, so there is no classification. Okay? And maybe as an outlook, let's say what I didn't told. So in my whole talk, I was assuming that this L defined the vibration of the horizon. It turned out that there are interesting, physical interest, no, let's say physically interesting, cases when we have cosmological Cauchy horizon, for example, in tau NAT, and then this L does not define vibration, but it's winding along some compact surface. So in this case, was a bit analyzed. So all axisymmetric solutions are known in dimension 4, so for n equal to 2. But I would say it's even below this case of the presence of electromagnetic field because it's really not much known beyond the classification of axisymmetric solutions. Okay, so this is all my talk. I also only organized and asked me to remind about Pau Square conference. So I put here, I hope I didn't mix the date. Oh, thank you.
Thank you very much. So in principle, the time would be up and no questions. But I was informed that our schedule is a little bit more relaxed later in the morning. And so we have time for 2 or 3 questions. Please, if you have questions, put up your hand. Yes, in the back there.
Hi, thank you. I'm wondering, is there any subtlety in quantization of extreme isolated horizon? Is there any subtlety in doing quantization of extreme isolated horizon?
Is there any subtlety in quantizing the extreme isolated horizon?
You said top.
Subtlety.
I don't know. So, but yeah, probably I'm not the right person to ask this question anyway. No, but do you mean? No, okay. I don't have anything clever to say.
More questions?
Maybe someone has comment on that, but maybe Abhay.
Or comments, that's fine. So I have a question. You mentioned that one quantity was the equilibrium distribution of a Brownian process, right? So that means it's a thermodynamic quantity of some statistical system. And now, of course, I will ask if this has anything to do with isolated horizon thermodynamics.
This is a really good question, and the answer is, I think no one knows.
Okay, that's a very
good
answer.
It would be maybe it would be good to so it might be that it's just the coincidence because it's okay. So you have some equation, you can interpret it in this way, yes. So it might be that it's coincidence, but we know that very often things that look like coincidence are not coincidence, and then it's giving us some deep understanding of things. So but I don't know.
Thank you. We have time for one last question. Yes?
Wojciech, I've always thought of the extremal case as sort of unphysical. You know, if you think of extreme Kerr, there's no physical process that could rotate you up that high.
But I think yes, I think it's not true.
Okay, that's what I wanted to ask. So in 2 parts, can you tell me how it could be physical? And then in the second part, even if it weren't physical for a second, would it help me to classify spacetimes? Is that the point? Is it like singularities and differential equations help me to classify solutions? Is it analogous in some sense or not?
So which question I should answer?
One first.
So okay, so there are some works that showing that by throwing physical matter into non-extremal black hole, you can get extremal horizons. Okay, so apparently it's possible. So of course you need to tune it very well, but you can achieve that. So there's some. It's quite. I think I learned it from Abai. So there's,
2324, that actually you can, the third law of black hole mechanics is false. And this is an important thing that many of us never believed it, but in classical general relativity, it is false. You can actually perturb, non-linearly perturb the black hole so that, extremal black hole, so that it becomes non-extremal, or a non-extremal black hole so that it becomes extremal. You cannot go super extremal. There is no naked singularity, but you can go from, any sub-extremal to extremal, and but surprisingly also from that's less surprising, from extremal to non-extremal.
And it's not fine-tuned?
No, it's an infinite dimensional data set. And since you're asking the question, there's a lot of confusion on this because people are doing only linearized waves that are going in, but these are full nonlinear general relativity. They are small data in the function space sense, just like the Christodoulou-Kleinemann kind of analysis. So they are small but infinite dimensional data sets, which actually non-linearly, full Einstein's equation, will take you from extremal to from sub-extremal to extremal, and vice versa.
Thank you for the clarification.
so of course, understand there is special matter, yes. So like the loss of equations or the scalar, I think, but you can achieve that.
Thank you.
Yeah, thank you very much for questions and comments, and thank you, Wojciech, for your talk and for answering them.
Thank you.
Thank you.
So you know that's in the